Uh, okay, so in this part of the MELTS lecture, what I plan to do is give an global overview uh, about how polymer materials, which are solid, and if you heat them, they melt and become liquid-like, how they behave. Uh, at lower temperatures, they behave glassy, and what does that glassy mean, etc. Well, you can understand and refer to figure out the meaning of glassy behavior and so on and so forth from the other lecture, which focuses on structure factors, G of R, how to measure a glassy behavior, what are the typical characteristics. Here, I shall assume that you already have an understanding and try to give a bigger picture. Typically, this is not what you get from a polymer physics book where they say, okay, you have polymer melts, you have only polymers and they are fluid, um, and what should be its properties. But you know, the plastics that you see around are not always melts, right? So some of them are solid, like the plastic bucket or the mug I was talking about. So what I intend to do is use this more of an engineering book to give an idea about how polymer, I mean, dense polymer uh, materials behave. Uh, and then the statistical physics of it is considered. I mean, the physics part of it is typically considered only the liquid perspective, but not all polymers are liquids, right? So I want to give a bigger picture. We talk about glassy polymers, but we don't know how to, I mean, sometimes the whole phase diagram is not clear. So hence this discussion is primarily from this book, okay, which gives a bigger global overview. It's an engineering book. So the other thing I have in mind is the other thing I have in mind is to talk about stress strain behavior of a general material, and this is often which is not focused on in much focused on students forget, at least for the physics courses, whereas this is very standard stuff for engineering students. So whenever you have a material and you subject it to strain, uh, yeah, and then some stress develops, and if uh, if for small strains, if you release the strain, uh, the relation between stress and strain is first of all linear, and the slope of stress by strain gives you the Young's modulus, and you have elastic deformation up to a certain point, so you can deform a material, okay, up to a certain strain value called suppose the yield point. And if you strain the material such that the amount of strain is less than the yield point, then you have elastic deformation so that the material comes back to its original shape and size and length after the tensile force is removed. So tensile force is basically a force which is applied, which is used to increase the length of the material along a certain direction. The consequence, more often than not, if, especially if volume is conserved, the material basically undergoes deformation to decrease its dimensions, its length in the directions perpendicular to the direction to which tensile force is applied. If you're applying force to uh, decrease the length along a particular direction or axis, that's a compressive strength. Okay, so let's coming back to this figure. So after you cross a certain yield point which defines the limit of elastic deformation, you have plastic deformation. Means that if you go beyond this strain, if you apply strain, you apply stress and you get strain, or you apply strain and you measure the stress, vice versa. If you apply strain such that the amount of strain is beyond the yield point, then the material is not going to come back to its original shape and size. There has been some plastic deformation. It's not elastic deformation. It's not going to come back to its original shape. And the stress strain behavior typically looks like this. There's a certain peak, and if you increase strain beyond this point, called the ultimate tensile strength point, that's the maximum stress for deformation that the system can handle, is the most stress that the rod can handle. So after this point, what you get is, as you increase strain, the stress actually decreases. Necking occurs. What is necking? Basically, the material becomes thin along a point, the stress decreases, though strain is increasing, and finally, beyond a certain point, you get fractures so that the system breaks into two. Now, you should also realize that basically, though we talk colloquially in terms of tough, a material being tough, strong, ductile, brittle, and hard, actually, these things mean different things to engineers. Okay, and gigapascal is 10 to the power 9 pascal. So, what is tough? Tough is resist failure. Failure is fracture, even after deforming. So basically, if you have a very large this area, necking area, and so on, even after deformation, you resist fracture, failure, if you like. That's a tough material. But a strong material will have a very high Young's modulus, so that it will resist both deformation and failure. Okay, ductile is, it will have a very long deformation regime. It will neck a lot before it breaks. Brittle is, it will rather break before it deforms too much. So basically, this region will be small, and then immediately thereafter you will get fracture after a very small plastic deformation and necking region. And hard is under compressive strength, resist dense scratches and other permanent changes under compressive force. And stiff is, it will resist deformation, any kind of deformation. Now, the difference between metals and polymers is that in metals, once you heat them, they become liquid above a melting temperature called Tm, whereas polymers do not have a sharp melting temperature. As you heat a polymeric solid, it becomes a viscoelastic solid, in that it shows properties of flow as well as that of solid. Solid means there's a shear stress. Flow means basically you have a shear stress, but only under a strain rate. There is a strain rate. You don't have a deformation. You have a flow. You keep, if you apply the slightest of stress, the strain will completely go on increasing, so that you get a strain rate. So polymeric solids under heating show viscoelastic behavior, and finally it becomes a viscous liquid. But that actually depends upon the microstructure, and we shall discuss this a bit. And that cross-linked polymers, they don't become liquid at all. They tend to flow to some extent, but finally, though, you can never bring it back to its original shape. But again, it also doesn't become a liquid polymer. So some amount of shape is maintained, and it can handle shear stress, though it can deform a lot. So cross-linked polymers, they would rather deform rather than flow, whereas non-cross-linked uh, polymers can become viscous liquids, with high viscosity. And you can also have rubbery flow, which means slow deformations at extremely long time scales. Yes, but it can still handle shear stress. It won't flow like a liquid. So before talking more about polymers, just to give you an idea about about the Young's modulus of different materials. What is plotted on the y-axis is the log of the Young's modulus in gigapascal units, and on the x-axis is the density. And one of the highest Young's modulus materials is diamond, with around 1000 gigapascals, 10 to the power 12 pascals, with a density of around 3. It's diamond, as you know, is carbon, so it's not surprising. On the other hand, metals are also quite strong and hard. They have rather have high Young's modulus, to the extent of around 500, 300, 500 gigapascals, but their densities can be much more, in terms of kilograms, 1000 kilograms per uh, meter cube, right? So this is the unit. If you like, grams per centimeter cube, you can also use that. It's megagrams per meter cube or grams per centimeter cube. It will have densities of greater than 10. It's not uncommon for metals, right? And they also have Young's modulus rather high. Comparatively lower in density but similar in Young's modulus are the so-called ceramics. What are ceramics? They are often oxides, right? Just read up the class of material called ceramics. They are less dense but equally tough and hard, and so on and so forth, with high Young's modulus. Even lower in density are the silicate glasses like sand. They are glassy materials, but they have relatively low density, similar to that of diamond. Uh, but they are also like 10 times lower Young's modulus. Compared to that, look at polymers. They are around 10 to the power 5, 10 to the power 6 times softer. So if you are talking of polymers, foams, they are even lower than density of 1 grams per centimeter cube, whereas many class of polymers is around 10 to the power 5. Look at the y-axis, 10 to the power 5, 10 to the power 6, softer than hard condensed matter materials, which typically fall in this regime, right? And you can have some systems which are even softer, which is colloidal solids and so on and so forth. We're just giving a broad idea. So you see, engineering polymers are somewhere here, gigapascals, and many of the others called elastomers and silicon and soft, whatever, butyl, etc., are even 10 to the power 5 times lower Young's modulus. With this, I will basically very broadly. So we are all talking not of polymer solutions, but polymer materials, which are just full of polymer chains and nothing in between. And broadly, the terms that you typically come across, less in physics, but often when you need to read papers, you want to be aware of these terminologies. And they are called linear thermoplastics. Basically have linear polymer chains. They can be branched, uh, but there are no crosslinks. And those are examples are polystyrene, PMMA. There's a big full forms. Don't remember, just look up Google. Polymethyl acrylate, something like that. PE is polyethylene. Another term that you come across is HDPE, which is high density polyethylene. So these are basically very long polymer linear chains. They can uh, they even if you heat them, the viscosity can be very high because they're very long, and they and can be entangled. These things can be locally crystalline. Okay, but they're typically amorphous materials at low temperature and liquidy at high temperatures, and that they can flow. They're still amorphous. So these are called thermoplastics. These can typically flow at high temperatures. Once you melt them, even before they get burnt out or something like that, before there's a chemical reaction, they can flow. They are melts. The other kind of material is the so-called very highly cross-linked thermosets. spelling is wrong. Thermosets they are called, and they are typically things by which polymeric material, and they have tons and tons of crosslinks. I mean, every second, third, fourth, fifth monomer has a cross link, and these are the things that the fevicol and gum are made up of. So when you expose them to air, what you happen is these hard, large number of crosslinks develop, which makes them very hard. Okay, so these are epoxy and crosslink thermosets, I think it is called. The third class of material is so-called elastomers. They are more like this type of material, but they have a few crosslinks, few and far in between. So they can flow, but they can basically behave like this. They high temperatures, but then finally they are crosslinks, so they cannot flow endlessly. So in that sense, they are somewhere in between. These are hard because they are very high density of crosslinks. Crosslinks are chemical bonds, right? The special thing about these two class of materials is that they have glass transition temperature, uh, TG, in the order of 50 degrees centigrade or 100 degrees centigrade room temperature essentially, whereas elastomers are materials which have room temperature, which have TG well below 0 degrees centigrade. So it's more like -50 and so on and so forth, so they can easily flow at room temperature of 27 degree. They are very easy to deform, whereas these will be relatively easy to deform after you go above the glass transition temperature, which will be anything about 50, 70, 100 degree centigrades. These will of course have even higher. Typical densities of polymeric materials, melts and solids, no solution, is order of 1000, 2000, 3000 kg per meter cube. They are after all made up of carbon and hydrogen and a few other elements, nitrogen and phosphate thrown in between. So they are not made up of tons and tons of very heavy materials like metals. So basically their densities are typically in the order of 1 grams per cc, 2 grams per cc, 3 grams per cc, which when you convert into kg per meter cube, it's this order. Metals are one order higher. Okay. Now looking at the, uh, so here what we are looking as is the Young's modulus. Okay. Of course, a log scale. Uh, so basically 10 to a 6 Pascal scale, and here this is normalized temperature with respect to T by Tg. Why is it plotted like this? Have a look at the glass transition, where we discuss glass, and here the temperature is given in real units, that's in centigrade. And this is how the phase behavior of thermoplastics behave. Uh, so what does this show? This shows that they have a glass transition temperature of around 100 degrees centigrade, 40, 50, 100, 150, whatever. And here they have weak van der Waals interaction between the chains, large number of weak van der Waals interaction within the chain. So there's a lot of interaction. That's why to make them flow, you need higher temperatures. Whereas for elastomers, there will be a lot of vacant space between these chains relatively, but not any solution. And that's why they have a glass transition temperature of relatively lower, -70 degrees centigrade or so. So here they have basically, so basically you have a Y, Young's modulus of 10 to the power 6 Pascal, if that's the unit. So that's 10 to the power 4. So basically around 1 gigapascal, and around 100 degrees centigrade or so, you see that the Young's modulus rapidly drops by how much? By 4 orders of magnitude. And thereafter, at slightly higher temperatures, it can easily flow. So you see slow change of force and liquid-like response, and Young's modulus drastically drops here. Yes, if you increase temperature, quick change of load, you can also see a rubbery region in terms of uh, Young's modulus means that as you increase temperature, the Young's modulus increases. Why does it happen? That's because of the entropic force, right? Polymers have show deform. I mean, uh, basically, they don't want to deform, because if you pull them, the number of available conformations decrease, so free energy increases. So the origin of elasticity for polymeric materials, rubbery, is basically uh, entropic in origin, and if you increase the temperature, this uh, force to come back to its original shape, that would increase. So basically Young's modulus increases with temperature, and that's the rubbery regime. Uh, Rubber elasticity, it is what is called. And you see a very short small rubbery regime for thermoplastics, and typically tends to flow above the glass transition temperature. There's a big drop. So this is how and this is the glassy regime. So if you discuss glassy polymers, this is where you are typically talking about when you're talking about thermoplastics or amorphous plastics. On the other hand, if you have thermosets, which are the highly cross-link regime, what you see that at small temperatures, they still have 10 to the power 4 as the Young's modulus. I want you to note this. The units is meganewtons per meter square, right? So it's not gigapascal. So you still have that, but they are highly networked. They are highly cross-linked. There are large number of chemical bonds between uh, monomers of adjacent chains. As a consequence, they have even a higher uh, transition temperature, higher than 100. It can go up to 200, and they have a relatively small drop in the Young's modulus once you cross the glass transition temperature, right? And this shows the relaxation time. So you are changing temperature slightly, but the relaxation time can uh, change, right? Um, so I'm not sure whether this is the relaxation time. I have to check it up. Just I think, yeah, this is 10 to the minus 4, 10 to the minus 2, 1, and yeah. So as you go down in lower in temperature, you have a higher relaxation time. That makes sense. Yes, this would be the relaxation time, which will be also related to the viscosity, by the way. So what is the message? In the small change in temperature, you have a huge change in viscosity or the relaxation time. Now here, this has a very large rubbery region. Now, because there are so many crosslinks, they cannot easily flow. It never really goes into the viscous flow regime. Viscous flow will be this regime. But if you increase the temperature, instead of going into the viscous flow regime, it rather has a rubber elasticity region, and even at higher temperatures, Young's modulus, yes, decreases as these various bonds break, but I mean, there are large number of crosslinks, so basically it never really flows like a liquid. So large rubbery region, low flow, slow deformation at very long time scales. Y increases with increasing T here, and this is the glass transition regime, and there's a huge change as you see even on a slight change in temperature. These are thermosets, highly cross-linked. Polymers, the last class of material, is basically what we call as it's elastomer. This is basically elastomer. You have large polymer chains, and they are once in a while over a large segment of a polymer chain, they are connected by cross links, and here they uh, and since there can be large spaces between adjacent chains, there aren't too many hydrogen bonds or van der Waals interaction. As a consequence, they have a Young's modulus, yes, of 10 to the power 4, like 10 gigapascals or so, but at a temperature of around minus 70 degree or so, there's a large drop in the Young's modulus, well below 0 degrees centigrade. This is the glass transition temperature. This is not the melting temperature. Remember, because because even at small at lower temperatures, it doesn't get into a crystal. It still gets into a glassy state. It still remains amorphous. And here there are crosslinks. In that sense, you have a rubbery regime in that the Young's modulus increases with temperature. This is the so-called melt regime. Again, this is the melt physics regime. This is what physicists typically study. But these polymeric materials are often also glassy, which is glossed over in physics book. So here you do get some viscous flows much higher than the glass transition temperature in that it flows, but finally there are crosslinks. So you have a very wide rubbery plateau, whereas in the other cases you have much smaller rubbery plateaus. If you remember, it is 1.2 and so on and so forth. Here you have they can flow under small deformations till they hit the crosslink. The polymers can slide past each other, right? So you have a rubbery regime and viscous flow here, but finally there are permanent chemical crosslinks, which the polymer has to take care, so it cannot flee uh, infinitely like water or a simple liquid. Right, so that's what I wanted to say. Now, after this, we're going to primarily focus on this regime in the discussion of melts. I mean, like, we're not going to talk about glass, that's a separate topic. Okay, and you can talk about liquidy polymers for elastomers, or typically we don't talk much about uh, but we also thermosets, but we talk about thermoplastics where things are entangled but no crosslinks. Okay. So with that, we'll end this module. Basically, the idea is to give you an uh, yeah